Hi, let's see now if in this next section of the video about the system that is for controlling the classroom luminaries with simple push buttons, and now explaining the part 3 on development and the part 4-5 on testing, you see, we can go to the end. So the final idea here, is to generate a kind of a circuit like this, developed and synthesized in a given target file, a complex PLD or an FPGA, so that you can try for real later using a prototyping board how it works for real, right? So let's just start this developing and testing functional and gate level. So in the end we can also get some measurements about the speed of the circuit for a given target chip. Well, so this is the tutorial that we are working on, so let's go down to the developing section. It's the specification section, the timing diagram, the plan, and the idea of placing all the circuit inside an architecture of a finite state machine, the planning of every single component of the finite state machine, the CC2 for generating the outputs, the CC1 for calculating the next state to go, the state register based on data flip-flops to memorize the current position of the machine. And so in the end, from this picture, you have a circuit, okay? And if you have a circuit, naturally, the next step to go, if everything is clear, okay, is, as you can imagine, the translation of your design into a BHDL file. So this is what goes here next in this third developing section, all right? And as usual, okay, you better find something similar to copy and adapt. And for example, you can go and visit, for example, this bike flashing lamp. And that, it's about lamps again, not classroom luminaries, but lamps again, the one that you may have in your bike. This idea of clicking the push button one time and having the option to switch on the lamp, or clicking again and have a flashing situation of the lamps, and something like this, okay? And another time, and then it goes off. So if you already have a tutorial like this, with everything organized and solved, naturally, what we have in mind now is not that different. But fortunately, because this is a tutorial, the light control BHD, that means the translation of every single file, every single circuit that has been discussed previously in the plan, is already here. So the only thing now is to start a new project, for example, in this location, and get everything ready for compiling this single file finite state machine for a given target file. That is what we are going to do now, right? So let's just start creating the light control folder. So this is CSD P6, and here in this P6, new folder, light control, that way. And here is where to save the file light control BHD. So save the link as, this is LCSD P6 light control, save. So that now that it's time for just running Quartus Prime. So this is the Quartus Prime file, new, file project wizard, new project wizard. Next, let's find the location. First of all, it is LCSD P6 light control, that's the location. And now the project name, light control PRJ, and the top entity, light control. An empty project. Let's add the file that is already here. And let's find, for example, the Cyclone 4, or if you like, the Max 10 that is available from the D10 Lite board that can be found here in electronic devices, Intel chips, and that one, for example. Copy and paste that chip reference into the window, and this is the chip that you can highlight. So that's it. Next, and as usual, simulation model SimAltera and VHDL. Next, and this means that now the machine is interpreting the file and trying to organize the project. So if everything is all right now, you see the project is this file where you see the entity definition, and then the architecture of this entity like control is basically a finite state machine where we have translated first of all the state register like this, exactly the same way all the time, a synchronous state register with clear direct and clear that way, and then two combinational circuits described by means of a plan B, the truth tables transferred to a process that is a kind of a case, and that is especially convenient here because you have a when separating every single state in which you have arrows to determine, for example, which is the next state to go. And then the same thing happens for the CC2 process, and this time is even simpler because you only have to do one kind of operation at every state. So you can use the same plan B to design this combinational circuit 2. And this time is that simple. K is idle, Z equals 0 because you are waiting for someone to click. The next state, click one detected, it means the same Z. And when you release for the first time the button, it's still Z equals 0. But when someone clicks again, now Z goes high, and so on and so forth, right? So this is the translation of the finite state machine into VHDL. So now it's time for running the synthesis process. So if the process finalizes correctly, you see that in the end you have, for example, total registers 6, because probably the machine, because you have not said anything special, the machine has adjusted to the best method that it can find. For example, this time if the machine is using 6 register flip-flops, this means that it's using, guess it, right? One hot internal coding style for every one of the finite state states. You can do it in another way, choosing, for example, binary or gray, and in that case, you know from the plan that the number of registers has to be only 3, because using 3 bits you can encode up to 8 different states in binary. But this time, the number of registers is 6. So let's inspect before making any change here or recompiling that with another parameters. Let's investigate about the RTL. Let's see if it is looking like what is expected. Well, that's the picture. You see, it is like a single box that can be opened like this. So here the machine is showing you the state diagram that has been captured. Okay, every single arrow and state transition, whatever it is, a loop or it is a state transition, doesn't matter. You see, the machine interpreted, and here you are, the spreadsheet explaining every one of the states and transitions. Okay, that's the way it works. And then if you like to see the binary encoding, you have that encoding, which is pretty much, you see, a kind of a one hot with the particularities of this code taken by Intel. In some way, 6 states means 6 different codes, 00001, 00010, and so forth. Okay, so that is the RTL. And here you may like to see precisely that Z, or this OR, is perhaps the combinational circuit 2, and the combinational circuit 1, along with the state register, it is taken as a single block by this, by this drawing. So perhaps to get a better picture of the final circuit, perhaps it is better go and investigate not the RTL, but the other one, the technology map, okay, like this. Let's see now what happens. We have to be able to inspect now for real the 6 flip-flops. So if you go zooming, you see, you have one flip-flop generating, you see, the current state 2, and well, you see, you have then logic cells to implement the CC1 section for, you see, generating this wire, for example, here may be very well labeled as the next state, one wire of the next state cable, right? Here you have another wire for the same next state. So you see, you can visualize them quite well. So this is 1, 2, 3, 4, 5, and 6 flip-flops. The 6-bit memory cells that are memorizing, you see, are saving the current state of the machine. Then probably you see that one is basically this logic cell here is the CC2, because the output of this logic cell is for generating the Z. So now here you can understand very well that these logic cells here, they are separated as individual 4 input boxes, but it doesn't matter. The 6 of them are for implementing the CC1. That's another way to see that. So it looks like quite right. So the next step is to check whether this circuit works as expected or not, implementing a test bench. But you see, before going to the test bench section, the section 4, perhaps it's a good time now to see whether you can implement another kind of circuit based on binary encoding, something like that. So to do that, you may clean your project and go to assignment and change the settings. Let's impose a given and a specific encoding for the state. So here you can click the settings, and now what we are talking about, remember, instead of fixing the EDA tool setting simulation, now we can pay attention to the compilation process or the compiler settings. You see the compiler settings, and here you have some optimization mode, that let it be like that, balanced. But here you are a long list of settings, advanced settings for, you see, synthesizing the circuit. So if you click here, you have plenty of different kind of options. So you can be very professional here, trying to get the circuit that you like most. But now we will pay attention only to the idea of encoding the finite state machine using binary, gray, or one hot at the circuit, at the previous circuit that we have synthesized now, that was taken by default by Quartus Prime. So now if you say states, for example, the many options and the many possibilities here are filtered, and what you've got here, you see, is 4 options or 4 parameters related to finite state machines. For example, extract the VHDL state machines, it is set on. Extract very log state machines, well, that is not of importance now. Safe machine state is something that implies covering all the unused combinations for a given code. but that is not of interest. But this one, yes, you see, state machine processing. Instead of auto, you see, that has meant, you see, in this design one hot, we will choose now, for example, binary sequential, because now we are using binary and we synthesize the process. We are sure that only 3 registers are taken for to be considered as memory cells. So if we say OK, you say apply and OK, and you can recompile it all. You still remember? It goes like that: project and clean project. When you clean project, you can start again a new compilation. So after synthesizing, we have the same project now, but you see only 3 registers are used for the same purpose. So now we can watch which ones or how it looks like the RTL again. Because this is the advantage, you see? From the RTL point of view, nothing happens because the internal encoding of the state is something related to the technology. Functionally speaking, you have exactly the same RTL. Okay? The only thing that has to change here is the capacity of the state register. So let's go and inspect by means of the tool netlist viewer technology map. So you see, the technology map now is different. It has only 3 flip-flops, and this and this and this. And the 2, you see, 3 flip-flops and 3 logic cells for implementing the state register and the CC1. Okay, is that so? And the CC2 probably is different as well, because from the CC2 is depending on the internal state. So this is the current state. Exactly, you see the current state, the output of the flip-flops are the ones that are taken as the inputs of the CC2, so that from this circuit, this combinational circuit, the Z is developed. So it looks fine, okay? It looks fine. Then there is another option that I may like to commend you, but it's not that important, and let it be as it is by default. But if you like to see what happens when you switch the option, you will see what happens. Okay, so if we now start again, if we go to assignments and settings and compiler settings, you know, the advanced setting synthesis, let's select of the many options state, you know, let's talk about this. This is the one that we have changed now, so let's change the other one. For example, the extract VHDL state machines. If you say off, what is going to happen is that the machine will solve the circuit but not thinking about the state diagram, and that's a great disadvantage for us. But you will see what happens now. You say OK, you will see OK, and now let's rerun the compilation process after having cleaned the current project. So the same project has been resynthesized again, and now you will see that the tool netlist viewer RTL is different, because, you know, it is like that, you see? There is no way to go to the RTL has not been interpreted as a finite state machine, but a regular circuit. In some way you have what is the CC2, the CC1, right? This is the next state to go. This is the current state. You see the feedback path that goes to the CC2 and the CC1 block very well. But from here you cannot extract what is of the most importance now, which is the state diagram, that is, you know, the brain of the circuit. So you cannot see that now if you click the tool, the state machine viewer, you see? There is no state diagram, which is, you know, confusing. So even if you see here perhaps a better picture in the RTL, you know, in the end, the technology view is the same. This is what I like to remark here. If you go to the technology view, which is the final circuit downloaded to the machine, that one is the same all the time. It is like in P1, in chapter 1, when we invent the circuit in many ways, plan A, plan B, but in the end, in some way, the technology view of them all, it looks like very similar. Not this time. Okay, well, the same now. You see, the technology view is practically the same, but not the RTL. And now here, there is this concept of a state diagram that is fundamental, and it is good to keep it so that you can check if every single arrow and every single output has been correctly interpreted at each state. So this is why you have to go and do not touch this assignment. Settings, you see, compiler settings, and when you click state, you better say extract VHDL state machines. You say yes, okay, you can say on. And now, well, if you like sequential or gray, doesn't matter. Let's use another code now, because just as a final example, let's use gray to code the internal state, the 6 states that we have here. So we will do that this way, okay, and apply, and okay, and now rerun. You see, this is project, clean project, and now let's rerun the synthesis like this. So you see 3 registers in gray code. So chip netlist viewers, RTL view, and this is again the same picture of the RTL. And now, yes, when you click here, you have the interpretation of the state diagram. This is what we like here. And if you see the spreadsheet showing transitions, those are the transitions, and the encoding, you see the gray code. All right, so something like this. You see 0, 0, 0, 0, 0, 1. This is the idle. This is the click. One click detected. So for this code, for this state, we are using this code, and then the next code in gray is 0, 1, 1, and then 0, 1, 0, and then, you know, we like to go like this, reflecting the codes. So this is 1, 1, 0, 1, 1, 1, and so on. But that's enough, because you need only 6 states. So you see, this is the last click, 3 detected. That way. All right, something like this. So now, yes, if this is the ideal circuit, let's see if it works using a test bench, right? And to work through the test bench, naturally, we have to run the tool that is attached to this simulation process, the RTL simulation, but better first, you know, generate the test bench template. Let's ask the machine to work for us this start test bench template writer. So that's the idea. So now if you are browsing your folder, you have simulation, model sim, and here you have the light control, Control C, and you move it just 2 folders above, light control here. And this is where you are going to paste that file. Let's change the name, light control, test bench. And now let's change BHD by BHD as usual. So that's another BHDL file, because this is the fixture where you are going to apply both processes now. You see, you have 2 processes to take into account. So this is the basic template. You see the entity, and then the architecture of this entity, the signals, and the component instantiation like this. This is the component under test, right? And this is the init, this is the instantiation, there is a very simple circuit here. We have only the component and the test, the instance 1. All right. So now we will replace that init and this always by what we have as a model to copy and adapt in the Digsys web page. So we will go back to our tutorial, and down there, right, in the testing section, this is the test bench you can open and copy. So, for example, first of all, we can copy the clock period, right? Control C, and let's save the clock period, 1 microsecond or 1 millisecond. If you say 1 millisecond, this means that you have, for example, 1 kilohertz clock signal, and so you may like to run for, I don't know, 20 or 50 clocks. So let's run for 50 milliseconds time, the simulation process. So we have enough clock periods to see what happens when clicking buttons. And then the idea of clicking buttons itself. And so what this means that you have to go, yes, here, right? But you have to go up to the, what? You guess it, right? Up to the picture of your timing diagram, where you are explaining the way that you are going to go clicking the button B. You see, you click the button, and sometimes after the initial clear direct idea, you see what you've got is that every clock rising edge, the device goes sampling values of this button, and sometimes it is for keeping the same state. For example, here you keep the same state idle, you see, but the next time you are detecting a 1 and then another 1 and then another 0. So you see the machine goes evolving. So this is what you like to check now for real in the computer simulation. So let's see if the circuit that is synthesized works very well like this. You see, this is the output that is expected this time. You see, the output goes high, the second pulls from the button B. So, you know, the only thing now is to translate this kind of a schema, okay, into VHDL test bench process. And one signal that goes all the time the same way is the clock. You see, the clock is, perhaps it is better to solve that using a single process for the clock, and then another process for inputting the clear direct and the button. You see, you can do as you like, but it's a good idea to devote a specific project or a specific process for the clock, because it's just, you know, a special signal that perhaps deserves it. So this is what you see in this picture, okay? In this file, for example, you can copy very well the clock process like this and paste it in the right place this way. You see, after instantiating the component and the test, this is the process that is related to the clock. This is what you like to do. For example, 1/2 period 0 and 1/2 period 1. But if you like, you can change that. For example, 2. You see, that's not a problem. You can change the shape of this waveform. For example, 2/3 of the period 0 and 1/3 of the period goes high. So in this way, the waveform, it is, you see, with a duty cycle of 33%, because it's, you know, 66% of the time 0 and 33% of the clock time 1. So you can do that very well, not a problem. You see, everything related to the clock period, and being clock period, the constant that you can change anytime. If you like to switch from 1 millisecond to 1 micro, you can do that easily. Just changing the constant and restarting the simulation. That's the good idea of this clock constant, the same that was min pulse. So here the same, okay? And then if this is the clock in this picture, very well, okay, if this is the clock in this picture, you can very well copy the other process, the clear direct and the button activity, right? So this is what is expected here in this sample example to copy and paste. So copy and adapt, you know. For example, let's copy the complete project process to the right place. And now let's investigate what we are copying here. Let's see if it makes sense or not. An initialization of 100 nanoseconds, that is not a bad idea. And then you see let's wait for a while, 3 or 4 clocks, and then you are setting clear direct and button to 0 and wait a while. Now here you drive the clear direct and keep the clear direct high for some clock periods, and then you see releases the clear direct so the machine can start. And now is when the user click the button B for the first time. This is like, you see, going to the wall and clicking the button. So in principle, nothing has to happen because you have to wait for the second pulse. So this is the first pulse. So let's hope that the first pulse is detected, changing the states, and then you release the button. So later on, you are clicking the button again. And now, from now on, is when you see, from now is when the light is switched on. All right, from now, because now you see at the rising edge of the clock, the B is 1 again. So this is the second click. This means exactly this one here, you see? Now you are rising, you are generating the second pulse, and here in this clock is when the light has to go on, because it's the second time, the second pulse that has been detected. So then you releases this button and wait, and then the third pulse, something like this. So from now on, you see, from now on, after the detection of this third pulse here, the light goes off. This is very well the translation. And then you know, when you are releasing for the third time the push button, the situation is again idle. Okay, and you can repeat the sequence. You see, that's the good thing about working with a text file that represents this picture. You can repeat that again. You see, you can have a second part of this diagram, or write another page representing some stimuli and trying to see what happens next. So this is something that can be added down there, right? So very well. Now we can switch that. You can save that, and you see what you've got here in your project folder. You have what is required. That is the entity and the test bench. So from both, we will design now the ideal simulation, because that one is the one that goes fast. So you can launch that from the Quartus Prime itself, run simulation tool, the RTL. And here is when you have to start a new project for simulating purposes. So you see, summarizing what we are doing here is that the device and the test is our light control. This is the test bench for the light control. Okay. The monitor where we are going to watch and discuss the outputs is the wave monitor. The signals that we have to connect is the output Z, you see, from the chip, the output Z, and the clear direct is the input, and here we have the button. This is what we are doing here, clicking the button several times and then generating another project, another process for the clock. So the clock is all the time activating the internal state register, letting the system go to the next state every rising edge. So let's see now if this works for real or not. All right. So in Model Sim, we have to do the same as usual. Now you are an expert on this. You see, new project. Let's browse for the right location. P6 light control. That's the right location. Okay. So the project name this time is light control underscore functional simulation. Let's see if it works ideally. And the work library, you know, the default library is work functional to detect it easily. That way. Okay. So now let's add to this new project the files that already exist. The light control, the unit and the test, and this one, the test bench, with the two processes that are going to stimulate the circuit. So that is what you've got, and now it's time for compiling this. Everything goes right. So very well, if everything is fine, you see, now it's time for you to start simulating and go into the monitor, the kind of a logic analyzer, okay? But let's start, you know, the functional simulation, which is down there, and the test bench entity. You see the name given automatically by this device is light control VHD TST. So that's the entity to simulate, ideally. As usual, we can organize now inputs and outputs conveniently using dividers. So add to wave everything in region. So you can do that, or you can better go and move down here because you are interested in the names, you see. So now a new divider outputs or output, and place the Z this way. Then the clock goes to the top, the clear direct, and the button, something like that. You can even add new dividers, for example, button, like this, or clear direct, or whatever else you like to subdivide here. That's right. So now it's time for running. We have organized the time, the clock period 1 millisecond, so this is going to be 50 milliseconds. That is right, so you say so. So now the machine has finished the simulation. Okay, so let's see if this is right. Okay, it's all right. So the machine is working as expected. This is what we have to see, you see. First of all, the system is unknown. Here the system has a previous value that has no interest, and this is where the things has to start running properly. So we see that this is in some way the starting time. Clear direct goes from high to low, allowing the machine to work sampling the push button. So you see the push button is high, then another time detected high, the output is yet 0, and then here you see there is it looks like that there is a coincidence, but it's not so. You see the clock is sampling a 0, so nothing happens, but then in the second clock, this time a 1 is detected probably. You see here it looks like that there is a coincidence, but it doesn't have to be like that. So in some way the output it's perfectly synchronous. You see, every time that you have to change the output, the output changes, if this is the case, synchronous with the rising edge. Like here, you see the clock has changed and the output has changed synchronously with the rising edge. Even if you have clicked, you see, if you have clicked for the second time the button, nothing happens meanwhile until the clock is detecting this one this time now. And then you see the light is kept high until another one is detected for the third time. So now this is the typical picture that you can go print and comment. But you know, this picture perhaps is not that completely interesting at all, because you see, you have to figure out what happens, only keeping an eye on the Z. Is there a way to do something better here? Yes, because you have the entity right here, you see, you happen to have the entity. So let me show you this idea, okay? You have the full architecture here, so why not to watch signals from all the architecture, right? For example, this is the top entity test bench. So you see here basically the button, the clock, the clear direct, and the output, nothing else. Well, the clock period is not even necessary, you can delete that. But you know, the signals from the top entity. All right. So what if I say that you go now down to the instance one, something like this? You see, you can go down to the instance one. And what is that you see here, right? The state register, the CC1 and the CC2. And guess what? The internal wires, current state and next state, that are very important in this kind of designs, can be dragged to the output wave. So now it's time to, you know, for example, go to the console and say restart, like this. So keep it all but restart, and now you see you have not only the signals of interest that are ports, but also here in your diagram you have the current state and the next state to be represented as well as the others. So why not run now the simulation again, run, I don't know, 50 milliseconds like before. So you see, look at this picture now. If you zoom it all, it looks like that. Now you have the same as before, naturally, respecting the ports. The signal starts. Now you see what is of very interest here, a highly interesting thing of getting represented the current state and the next state to go, and not using even the binary code, whatever it is, gray or one hot or sequential or whatever you like, but using the label that you have assigned to this state, which is perfectly right. You see, you have now that the system is idle. This time, because there is a rising edge on the clock, the system has gone to click one detected, you see, and so on and so forth. So you see now the very idea of the finite state machine running perfectly well. So if this is the functional ideal simulation, the next step is to go and run the gate level as an extra thing to see how it works for real. Okay, so this time you can imagine that you are simulating the RTL circuit, and you see the current state and next state are, and the levels are precisely from this point of view of the high level description by means of a state diagram and the like. So when we switch to the technology view and we switch to the gate level simulation, you will see nothing but the final ports and, well, many internal signals, but not the ones represented here as current and next state at this interesting level, where they can be represented using simple labels. Okay, that's what makes sense here. So this is the picture for you to copy and comment when, I mean for the report, when it works. You only have to do that part of taking a picture of this and commenting it when it finally works. Okay, and quite important, before quitting this functional simulation, we can, you see, the wave default organized and stated like this can be saved. You know that. So file, save format, so you can save like wave. So you say, okay, now it's time for quitting the functional simulation. So again, from the Quartus Prime tools, simulation tool, gate level, which is nothing but another instance of the same VHDL model sim simulator. So you see, but you have this advantage of starting again from scratch. Another project, this time gate level. So let's do that. Okay, so let's just start a project, a gate level project to simulate what happens in real time in the circuit. But you know, first of all, we have to go back to the Quartus Prime to see what happens and if the correct files are already there. Remember that now the simulation consists on the test bench file, the same as before, but then something else like the architecture based on the translation of the technology view along with the delay, the file that contains the delays associated to the given technology. So let's see what happens for real now in the Quartus Prime. Let's see in the design process everything went fine. Okay, for example, this is the full sequence of steps. The timing analysis has gone right, but in some way you see it is red, and that perhaps it's a complication. You see, you have that the models related to the timings are red, so something must happen here, and something is not fully correctly. Let's see, because we have the possibility now to run the timing analyzer and the EDA netlist writer. You see, the netlist writer is the one that translates the technology view into a file, the HDO. So let's see if this is right or not. Processing, start. For example, let's start the timing analyzer, and the timing analyzer looks like that it works fine. So now if we watch which is the parameter, the key parameter here, the key parameter is nothing but, see, timing analyzer, the time that it takes to go from clock edge to output changes, you know, that TCO. Time clock to output. So this is something that we can just get from this spreadsheet. You see the data sheet. Let's generate the data sheet information. Okay, the data sheet, it's here, you see. And let's report the maximum frequency and the data sheet. So now you see, and let's measure, you see, not the setup times, that is, you see, fractions of nanoseconds or just a few, very few time, whole time, but the clock to output time, you see, the clock port, it's like this. You are changing now the clock from low to high, okay, and the Z takes almost 8 nanoseconds to change. You see, that is the worst case scenario. So from this clock to output time, you can infer which is the maximum frequency possible. So 1 divided by this value is the maximum frequency. All right, you can do that very well using a calculator. So this is you may very well imagine that this is 7.97, so 8 nanoseconds. So 8 nanoseconds. So this is exactly 125 megahertz. That is the maximum frequency possible for this circuit. Because if you go faster, the output Z do not change accordingly, right? The system is still in transition and stabilizing to the final value. So now let's switch off this timing analyzer and let's see if we can see that in the wave, using the model sim gate level simulation. But you see, this means that we have to run the processing start, not now the timing analyzer, but the EDA netlist translator. Click, and let's see what happens. In principle, all the associated timing files for this chip has to be generated. But you see, you have two warnings here. So probably something went wrong, because the first warning is just the standard one related to the idea that we are not fixing the number of machines, the processors to run the synthesis, but the second one says something like generated the EDA functional simulation netlist because it is the only supported netlist type for this device. So we have a problem here, you see? We can simulate that device functionally as we did just now, but not at the gate level, because there is no way to get the translated technology view files. All right, so, and that is also here when you see the list of files, EDA netlist writer, simulation, you see, generated files. There is only the ideal one in some way, the VHO. So if you run that simulation, imagining that it's going to work, it's going to work, but again, ideally, not as something that you can just go zooming to a given transition of the clock and see how fast, how long does it take to get results at the Z. So what is that we are going to do if we have this limitation? Probably it is due to the fact that we are using the web edition of the Quartus Prime, which is free. Perhaps if you ask for the professional version, you are not going to get that warning, and the files are also generated for the Max 10 device, you see? So let's do something like that. Let's change the device from the Max 10 to the Cyclone 4E, the one that you see is not in this Terasic, the 10 Lite, but the one that is in the other one, the big brother. You see the Cyclone 4, so that one. Let's take this chip now, copy, and let's rerun the same project, changing the devices. You see, Cyclone, family, and now this device here. All right, so you see, this is the chip that we have in mind now. And let's say, okay. And now, because there is a new chip, it is better to say something like project, clean everything on this project, and rerun the synthesis from the very beginning, okay? But be sure as well, before, resynthesizing, be sure that the options are all right, placed correctly. So assignments, settings, this time you like to generate everything, so it's something like this. Simulation, you see, EDA tool settings, simulation, you can click here in this box, more EDA netlist writer settings, and here you have to check that everything is off. All right, so everything is off, because if you say reset, you see that one goes on, so switch it off and save. And now apply and OK, and now it's time for resynthesizing from this perspective. So the project is again here, the final result with 3 registers, and let's do the same tool, processing, or start processing the timing analyzer. And now let's inspect the tool, that is the timing analyzer tool, to recheck the speed of the circuit. So now it's time for going down to the datasheet, and in the datasheet we go, you see, that depends, perhaps that time, you see, this time it's a little bit faster, just 0.3 nanoseconds faster. So this is 7.63, but they're very similar to the other device, right? So here is not a problem. About 120 or 30 megahertz, the maximum frequency. You see, you go from the clock to the Z in 7.6 nanoseconds. So that is the way to fix the maximum speed. So let's switch that on, off, and now let's go to processing, start EDA netlist writer, you see, Let's see what happens now. It is like that. You see now, yes, it appears in green, the many files in which you have interest for simulating purposes. So you go to the EDA netlist writer, and in simulation you see generated files, and now, yes, you have many of them and several models. So you are interested precisely in simulating the light control VHO along with the light control VHD SDO, the standard delay output file. So let us start now very well with everything in place, the gate level simulation considering these two files, right? And the top test bench as usual. So now is when you will switch to the model sim and start the project. New project. Let's go to the right location, light control, Control C, okay, light control. Project name is light control underscore gate level, sim or simulation, and then the library is work gate level. That way you say yes, and now it is time for adding files to this project. Precisely the test bench only at this stage. Open and say OK. And now let's add another existing file, which is not one but the simulation model sim VHO, light control VHO, right? That one. So you say open and you say OK. Close, and now you have them both, the top entity established like that as a translation of the flat technology view along with the test bench. So you have them both. So now it's time to compile them both. So let's see, 0 error. So now it's time for starting a simulation. Okay, start the simulation of this gate level situation or fixture, which means the gate level is the design entity. So you see the test bench is the same, right? Very well, let's keep the name. Right, so that's entity, but now you have to attach that, if you like to do that for real, what? Add the file SDO, which is in the same place, simulation model sim SDO. All right, but this has to be applied to the region that is defining the test bench entity. You see, the test bench entity has this name, light control VHD TST, and now you have that inside this top entity, you have in the architecture the instance 1. And this instance 1, the component and the test, is the one that has this file that models all the delays associated to this technology Cyclone 4. So you say OK, and now OK. So you see, very well, right? You say OK, and now the machine is going to start simulating this like that. So now if you like, you can get the previous wave do, you know, setup that you had for the functional. But no problem, if you do that, you will see that you will realize, you see that the entity I1 do not has anymore anything like current states or, well, let's see, or no, probably not. You see beat and I don't know what. So let's see. File. I mean, I can do that thing, right? Very well as before. You see, add to wave all the items in region. I can do that. Okay. But perhaps it's better to get it from the to the macro file that we already have here, the do. But be careful, because you see the current state and the next state are not longer available here. So they have already been deleted. So very well, we have it. So now let's run that thing. Let's run for 50 milliseconds. That's it. So you see the clock and the full picture. You see everything goes fine. One pulse, one clear direct, and then you see the output is here is very clearly undefined until you click the clear direct. So now while clicking the clear direct, even if it takes several clocks, which is the normal situation, nothing happens, and then the system goes to the stable state idle until one click and another click. Okay, and you see the second click is clicked here at this time, but this is not exactly the rising edge. You see the rising edge is just a little bit before, so now you have to wait practically a full period to take the Z into action, and now the Z changes. So now is when you can zoom to see what happens for real in the chip. So here is when you can go zooming, and let's hope that everything goes fine, you see. And yes, that's the point, you see. You have here edge, which is the transition from 0 to 1 in the clock, that way. Okay, this is the rising edge of the clock. So now you can add another marker just to signal the time when the output goes from 0 to 1. And that is exactly something that you can imagine very well, practically 7.6. You see, you know that from the timing analyzer. So here is another picture that you can very well print and add a discussion about it, right? So that is the end of the gate level simulation in some way. Okay, so you make room, white space to add some comments so that your report is looking very well like this. You see, you have to go to the end of this report, and here you have it, something like this. You see, you know, the final, if it is 8.28 nanoseconds or if it is 7.57, that depends on the specific chip that you are using. It is the technology detail. But you know, this is all about concepts. And this picture shows very well what is going on here. I insist on this. You have a clock rising edge now. Now it's a kind of time equals 0. This is when the B equal 1 has been sampled to 1. And this is when the Z changes really, you see. So it takes, as you see, 7.57 in your circuit now for the cyclone 4 to change. All right. So that's the end of this quite interesting and long tutorial about the final synthesis of a finite state machine and the functional testing and the gate level testing as well. Thank you.